So this is a really good page to start on. This was the first page the other day. I do want to remind you, this definition of sigma and pi bonds is going to still hold true. We're going to go into the other theory now, which is molecular orbital theory. And you're all going to be great at this because you get to use your notes. But a sigma bond still means so I usually ask this question on the midterm, and the mistake students make is they say a sigma bond means a single bond, and a pi bond is a double bond. That's not actually the definition. And that is not going to hold true in molecular orbital theory. My definition holds true for both theories because that is what the definition was, is that a sigma bond is when the electron orbitals overlap between the nuclei. And that's how most students think all bonds are. A double bond, though, the overlap is, that's what's showing here, above and below. So the pulsation is above and below the plane between the nuclei, which makes it stronger, but you can see it's going to make it really reactive because it's not between the nuclei. It's not in a nice, safe, tucked in place. All right, so that's this theory, the valence bond theory, came from Linus Pauling, and he was a biochemist. He was trying, this was before the word molecular biology came out, and so he was really one of the first molecular biologists. He was trying to understand how molecular shapes worked. So this theory goes with all the drawings of Lewis structures. And then there was another guy, because there's a problem with this theory. And the problem comes up, it's actually a really cool video. And if your teacher, the sun being out, spring term is awesome. And every day I go for a walk and there's new flowers blooming. And so your teacher is not preparing herself, but there is an awesome video. Maybe I'll find it and link it on, and we can show it on Tuesday, but it has to do with oxygen. And oxygen, it turns out, is paramagnetic. And this is the dilemma. So does anybody remember what paramagnetic meant? Somebody's got to help these two. Yeah, paramagnetic means unpaired. Now, if we do everything with this theory, if we draw oxygen, it works. Everything's paired up. But they actually can liquefy oxygen if you push it into enough pressure, and then they drop it through a magnet, and it's not a refrigerator magnet. These are like the really strong magnets, and the liquid oxygen will not pass through the magnet. And so the liquid gets stuck in the middle of the magnet. It's a really cool video. You can probably YouTube it, where you just Google liquid oxygen magnet or something. And so it won't go through there. And so why this theory doesn't work. And so somebody came up with another theory. So each theory has its place. Molecular orbital theory explains magnetism, and it always gets it right. It came right out of quantum mechanics. We're going to be doing orbitals. So remember orbitals from the end of last term? Those of you who had Chem 151, you're going to like this. You're going to be like, oh, yeah, this is cool. I know how to do these. We're just going to make them into molecular orbitals. So we did electron orbitals or atomic orbitals. We did it of one atom. We're now going to put two atoms together. And so I'm going to go through how they work. And then they're really simple. But it explains the paramagnetic versus diamagnetic. And that was actually really important because it explains, it was what allowed us to create computers, your cell phones. It pretty much explains how electronics work. The other theory can't explain it, but this theory allows the electrons to move around. The other theory, only in a resonance structure do the electrons move around. The advantage of the other theory, if we're dealing with something like hemoglobin that has 2,000 carbons, this theory, there's no way you could draw chart for 2,000 carbons. So the other theory works great when we get to molecules. This one works good for diatomics, like two atoms coming together. All right. So, yeah, and so I don't know if Major saw this. There's no notes because we're going to take notes on this page. And these pictures are important. And this is the guy who came up with this theory, and it does explains magnetism really beautifully. So periodic table. Let's do, we can do it for hydrogen. Let's do hydrogen. So we're going to do H2. So we'll just start really simple. Oh, and it actually does that over here. So the idea with this theory is on the outside, this is what this is going to look like, our picture. So on the outside, these are atomic orbitals. And so the atomic orbital in hydrogen is called a 1s. So on this side also we have a 1s, and that's an atomic orbital. So we'll just start like how I did at the beginning, really simple. And what happens is they come together, they hybridize, and you had two orbitals. So the sum of the atomic orbitals equals the number of molecular orbitals. And no, I'm writing too big. You always get one that's stable. So you're going to make what are called bonding. We get two types of orbitals. So one type is called bonding molecular orbitals. It's always abbreviated as MO. So you're going to see me just write MO. So bonding molecular orbitals. So MO means molecular orbitals. And the second type is anti-bonding. And I think I have a picture. I do. So bonding molecular orbitals are more stable. They're stabilized. So they have a lower potential energy. So this is a bonding orbital. It ends up lower than where we started. So we started here with each hydrogen at the 1s, and now we're lower. This up here is the anti-bonding molecular orbital. We're writing a lot right now, and then all we do is make these charts. But it's my attempt to explain it. And this picture over here actually has all this written. So bonding versus anti-bonding, MO. So we have to label. The bonding ones, they're either going to be a sigma or a pi because it's a bond. So we no longer call it a 1s. And that's true for both of these. Anti-bonding, we put a star with it. So we put a sigma star or a pi star. So you're going to see me use the sigma and pi symbols here. S's only make sigma. That's the only possibility. They can only overlap in between them. We cannot have a pi bond until we get to p orbitals. So this is labeled as sigma, and then we put a subscript of 1s. So the subscript is saying it was the 1s orbitals that came together. And then this we call a sigma star because it's destabilized. And I should have put that destabilized. It has higher potential energy. And then we say 1s. So whatever the name of the atomic orbitals that came together, that's what our subscript is. And the star means it's less stable. So what does that mean, more and less stable? So the bonding orbital is the overlap is between the nuclei. So just like we talked about, that's what this picture is showing you. Makes perfect sense. So you're going to love the anti-bonding. The electrons are outside. That's what this is showing. That's the anti-bonding. So there's only space for two electrons in between, and then the electrons start pulsing on the other side outside the nuclei. And as they start pulsing out there, they eventually destabilize the whole thing. and it ends up not working. So hydrogens each had one electron. So this is just one hydrogen. This is just one hydrogen. So they were 1s1, right? So you remember that from our periodic table, right? Hydrogen is just 1s1. So the number of orbitals, the sum of the atomic orbitals, it's the same thing for electrons. We have 2 electrons, same rules as before. You put the electrons in the lowest first, you pair them, 2 electrons per orbital, all the same rules. One spins clockwise and the other one's spinning counterclockwise. So they're in the same space. That's how, right? It brings everything together. This is explaining, and it's the same thing on this first page, is explaining how can you have 2 electrons in the same space? And it's that they're pulsing in opposite ways. So one's pulsing like spinning clockwise and the other's spinning counterclockwise. So there's always just those 2 possibilities. There's only 2 electrons, so nothing's in the antibonding. All right, this one's really simple. We're going to add pieces to it. Actually, we'll add that when we get down to here. If we gave the hydrogen a positive charge, actually, questions before I do that. We're not going to give it a positive, and I keep doing that. I have to get rid of this pen. It doesn't have an eraser. Let's give it a negative charge. A negative charge means we're going to add another electron. So it doesn't matter where you add it. We're going to add one there. And so now I'm in my antibonding. What the antibonding means is it's now destabilizing the bonding. If I gave this a -2 charge and we completely fill in the antibonding, the whole thing's gone. Completely destabilizes. So if you fill in the whole chart, so you fill in all the antibonding, all the pulsing that's happening on the outside ends up destabilizing the inside and the whole thing falls apart. Magnetism, paramagnetic, means you're going to have an unpaired. So H2 is not magnetic, and yeah, they can liquefy it and it's not going to work. Diamagnetic is what we had, which is they're all paired up. So 0 unpaired. So that's how it would work for hydrogen. So let's move into the P's. So does anybody remember where are the P's on the periodic table? Maybe. We're gonna do the 2 P's. So boron to neon. We can do this also with the 3 P's. So aluminum over to argon, but we're going to stick here. So just boron, carbon, nitrogen, oxygen, fluorine, neon. All right. So how the P's hybridize. I always do valence electrons. So let's do, let me see what I'm doing on the next page. Carbon, nitrogen. Sorry, I'm trying to remember what I did on the worksheet. Let's do C2. So we're going to hybridize 2 carbons. So carbon is normally, I'm going to write it up above just to remind you. So if we did a carbon, just by carbon, we would normally say, well, 1s2, but we can ignore that. 2s2, 2p2. We did this one the other day, right? So sorry, I find mine. So the 1s is filled, then the 2s, and then this is the 2 p's. So we have 1, 2. So we're going to ignore the 1s's because they're filled. We're going to do the 2s's and the 2 p's just because I want to show you the s's and the p's. This chart here, we're going to reproduce it. This chart shows all the way starting at 1, 2, and then the 2 p's. To me, the 1s's don't matter because they're going to be the inner shell. So this is just going to be the valence electrons that we're going to work with. So in the theory I did the other day, we have to look at all of them, And that's probably why I do this, looking at all of them, that in Linus Pauling's theory, the S's and the P's hybridize, and they all come out the same. In this theory, that doesn't happen. And so the S's, we'd have the two S's here, one on each side. So again, the atomic orbitals we show on the outside. And then the two P's, remember the P's have three orbitals? So this is my two P's. And over here, my two P's. All right. If you're an engineering major, you should have your little ruler out and make everything perfect. All right, so the S is hybridized. And you get a lower and a higher. So the bonding, when I sit up here, the bonding molecular orbital is stable. Its potential energy is lower than where you started. And this is going to be called sigma 2s. So S's always make sigma, and the subscript is just there. And then this one that's higher than where we started at the 2s is called sigma star 2s. So just like up above, we had sigma 1s and sigma star 1s. So now we just call it 2s's because that's what's hybridizing. All right, so it makes sense. We had two orbitals. We still have two orbitals. One is more stable, one is less stable. The P's, we have 6 orbitals. So when they hybridize, we're going to get a whole bunch of possibilities. It goes 2 and then 1. And those are below where we started. And then we get 2 that are higher and 1 higher. And let's just erase so I can fit this in. All right. So this is when you draw it, your atomic orbitals, mine aren't perfectly lined up, but you can see here the atomic orbitals, the bonding ones are lower than where we started, and the anti-bonding end up higher. So these are anti-bonding up here. We'll do them in a different color. So those are the anti-bonding. When you have 2 lines, it's always, it's 2, 1, 2, 1. The 2 lines is a pi orbital, and we call it pi 2p because it's the 2p orbitals that came together. And then the 1 is a sigma 2p. So this theory is really interesting, and it does predict always correctly, which is the part that's really bizarre. And it's why your computer works, and how they make the computers better and doping and stuff. It explains all this stuff. You have pi bonds before you have the sigma bond. So a pi bond again is what? It's not a double bond. It means that you start putting the electrons above and below the plane of the nuclei. The electrons are going above and below before you start putting them in between. That's what his theory says. And then these upper ones are going to be called pi star 2p and then sigma star 2p. So each theory has its place. Again, the valence bond theory really does an excellent job of explaining molecules, large molecules. This one, though, explains magnetic moment, and that's really that's what the technology age is based on. All right, now we're going to do electrons questions. You guys are all still in the what is she doing phase. So carbon, we're doing just valence electrons. If you want to do all the electrons, you would just include the 1s. So carbon has 4 valence electrons. So do the outside first, 2s, and then each 2p gets 1 electron there. And then here again, this is 1 carbon, this is the other carbon. In the middle is the molecular orbitals. So we're going to need 8 electrons because you had 4 and 4. So we combine it. Rules are the same as before. so 8 electrons. The diagram is always, so I keep pausing because it's not an always. The diagram is going to look like this. And you just have to draw the diagram and label it. You just do it one time, and then you have to answer a bunch of questions about it. And that's what we're going to do on the next page. So this page is about how to draw the diagram. And again, as Major said before, I did this last year in the classroom on the board, which is how I've done it for 25 years. So if you want, you can always go back and watch that video and see if that helps, although it really just takes practice. All right, that's 2 electrons. We go from lowest to highest. So this is lowest potential energy. And then we go up to highest potential energy. So there's 2, there's 4. And then here we have to put 1 in each one. So 5, 6, and then 7, 8. So first question I have for you, is this para or diamagnetic?
Dia.
It is diamagnetic. Because there's 0 unpaired. You're going to be asked that question, and so you're going to have a whole bunch. You only have to draw the picture once, and then you just count electrons. You want to do it with something you can erase. So you just have 2, 4, 6, 8. So it comes out diamagnetic. We're going to do bond order now. So bond order, it still means the same thing. If you get a bond order of 2, it means you have a double bond. If you get a bond order of 3, that's the highest you can get. You have a triple bond. Hey, somebody's wearing a mask at your work. It's the first person I've seen with a mask.
Because George here.
Right. All right. Bond order is number of bonding electrons minus antibonding electrons divided by 2. So if you want, if you have all the antibonding to match, so sigma 2s and sigma star 2s, these really cancel out. Again, I always show them because when we did the valence bond theory, all the stuff we did with Lewis structures, we get in the habit of counting valence electrons to do everything. And so I keep teaching this the same way. So I always show the 2s and the 2p. I fill it in that way because carbon has 4 valence. Students who do a shortcut end up counting them and filling them in funny. And so the sigma 2s ends up canceling out on here. So I have 4 bonding electrons and 0 antibonding. So I'd have 4 minus 0 and then divided by 2. So I get my bond order is 2. And again, we're going to do practice. That's what the next page is. And we get little charts to fill in. And some will have antibonding. So this will make sense in about a half hour. All right. So we're going to change this diagram. Is there any questions before I do that? Oh, actually, I have one more question. How many sigma bonds It is 0. You are absolutely right. So all of you who did that and I couldn't see, it is 0. Because there's nothing there and these canceled each other out. So this is a sigma bond and there's nothing there. So the sigma bond, this is saying there's nothing in between the nuclei. There's nothing there. But there's something above and below it. Like in my picture here, there's something there, but there's nothing in between. Really interesting thought. And it explains why things work. Some things. All right, pi bonds. A bond is 2 electrons. So how many pi bonds are there? Right? Peace out, 2. On this one, there is 2. How many pi bonds maximum could there be? It's 2. maximum sigma bonds is always 1. So the maximum total is always 3. Again, we're going to do practice on the next page. One more piece. We're going to do 2 more things with this. And I know your notes are probably all over. You can just do them on another page. There's something. So Omar, so that incorrect worksheet that I posted, it's the worksheet for next week, part of it. So he got to this question. Any of you who had tried to do that worksheet, it's going to ask you for the highest energy occupied hemo. So I'm going to write it over here. It stands for highest energy occupied. We had something like this before, but it's the highest energy occupied. Oh, we did HEO before. Highest energy occupied orbital. It's just the highest energy molecular orbital. So it's a HEMO now. And so it's the highest one that we have something in. So we would say sigma 2p. I'm sorry, pi 2p. My brain had it right. My words got backwards. Never happens to any of you. All right, questions. That's a lot of stuff. But again, they all come out. It's the whole thing is drawing the chart. And then you just fill it in. And so you have the chart there. And so we're going to turn the page if there's no questions. And we're going to do it with the next one. So I am going to pause for 5 minutes. If you want, you can take your 5-minute break, or you can try drawing the chart or counting your valence electrons. I'm going to give you a chance to try it or to just breathe for a minute. Oops. Oh, you know what? Another molecule is the molecule of the gods, theobromine. It's what's in chocolate.
Theobromine?
Theobromine. You're doing caffeine. Because
I know
that's
that.
your theobromine's my addiction. You can pick an addictive drug. You can pick like heroin, morphine. People have done some really fascinating. You can pick hallucinogens. All right, let's do this. So we can go through drawing it again because that will help you. So you start with your 2s on each side because carbon, nitrogen, we're in the second row. And then you're going to go one of the molecular orbitals is higher and one of the molecular orbitals is lower. So do this with something you can erase in case your skills are as good as mine. Try to make your atomic orbitals straight across from each other. The one that is lower is sigma 2s, and the one that's higher is sigma star. So it's destabilized. Again, it means the electrons are pulsing outside of the nuclei, not in between. All right, and then go up a bit and you put your 3 2p's. So again, that's what the S's are going to look like. Sigma 2s, sigma star 2s. And then up here, you put your 3 2p's on each side. Should bracket them. And then the lower ones, you're going to go 2 pi's and a sigma. So you can have a cherry pie and a pecan pie. Pi 2p. So the subscript is what is hybridizing, and the one by itself is a sigma 2p. And then your other ones have to be above your atomic orbitals. So 2 and then 1, and so pi star 2p and sigma star 2p. All right, that's beautiful. Questions to that point. They're all going to look the same. Actually, they're not all. Sorry, I keep saying that. When we do this one, we're going to break. Go ahead.
There's always 2 rounds, right?
I always do the S's and then the P's.
Okay.
because that keeps us consistent with counting electrons how we did previously. All right, now we have to count electrons. So we're doing carbon, nitrogen. So you're going to have 4 plus 5. So we need 9 electrons. So the question Major just asked was actually really important. And I mention this because a lot of you like YouTube videos and stuff. And there are shortcuts because these guys are going to cancel out. But the problem is you end up counting your electrons incorrectly. And so I do it this way because it's the same way we counted electrons for the past 2 weeks. We're counting valence. The negative means we have 10. So you're always going to have either a negative or a positive. So negative, right? The negative means you gain an electron. We're going to do a positive down here, so we'll lose an electron. When we draw this one, we're going to change the drawing. And that's why we're doing this one. All right. So we'll do the CN. I'm going to do it in pink. You can do, on this side, I'm going to do carbon, which has 4 electrons. And on this side, I'll do the nitrogen. It doesn't really matter. And the nitrogen has 5 electrons. Right? And then in the middle, I'm going to have 9 total. So 2, 4. Then you do 5, 6, 7, 8, 9. So that's what it looks like. You should have, now, count all your valence, and then these guys will cross out. So let's just talk about the CN first. The bond order. It's going to be 2.5. So I'm going to show you a trick to finding bond order. I'm going to show you 2 ways to do it. If you do your sigma and pi bonds, so there's 2 pi bonds. 2 electrons equals 1 bond. So 1, 2. Half a sigma bond. This is the weird part. This theory allows you to have half a bond. If you only have 1 electron in the bond, it's a half bond. In the other theory, not possible. The other theory allows you to have free radicals. So in the other theory, if we get an odd number of electrons, you can have an unpaired electron on the outside, but not in the bond. All right, if you add up your bonds, that gives you your bond order. It's an awesome trick. So the sum of the bonds equals the bond order. You can also do the thing where you do bonding electrons. If you Google it, it's going to give you this. Bonding electrons. I don't know why they give tedious definitions. Minus antibonding electrons divided by 2. So we have 5 bonding electrons. Minus, there's nothing up here yet. So 5 divided by 2 is 2.5. Or you just add these up, and that will give you your bond order. All right. Is it para or dia? Well,
Para.
sure looks like it's paramagnetic. So you have that one. All right. The hemo. So you usually just write the acronym. And yeah, your next worksheet's pretty short. Today's, yeah, we do get back into math the second half of the term, and so things start taking a little bit longer. But the highest one that has any electron, so sigma 2p. It doesn't mean it's full, it means it has an electron. All right, to do these questions, we have to answer the next one because we have to compare these two. Again, on your worksheet, when I'm asking which is the strongest, it's comparing the different choices. So it's not within one thing, it's comparing, in this case, these two. So to do the CN negative, I'm going to gain an electron, and so that's my extra electron. So now I have 10 electrons. So how many sigma bonds? I have a full sigma bond now. I still have 2 pi bonds. because I have a pair here now. So bond order is 3. Why is 3 the maximum bond order you can get? Well, if we added another electron, where would it end up? Up here. Antibonding means it cancels out one of the bonding that's just like it. So when you put one up here, you suddenly have to cancel down here. We can actually do that in a minute. All right, this one is diamagnetic because everybody's paired up. Highest is sigma 2p. So which one's stronger of these two? Stronger is higher bond order. So the CN negative has 3 bonds. That's always going to win. The longer one is the lower bond order. So you can just put a check or a star. That's fine either way. We're going to do one more and then we'll do this one down here. All right. So let's add to our chart. You can add on either side. We're going to do CN negative 2. So now we're going to have 11 electrons. So that 11th electron is going to go up here. So that's what's happening there. This is in the antibonding of the pi 2p. It changes your pi bonds. So your pi bonds are now 1.5. That one electron destabilizes one of the ones down here. You still have 1 sigma. And so your total is 2.5. So technically, the CN and the CN negative 2 have the same bond order. So they would both, for the longer, it would be the same as these two would come out the same. All right. Highest occupied would be pi star 2p. And it's now paramagnetic again. Questions with that?
So when you're counting 9 electrons, are you counting the bottom ones as well, or are you only counting the p's?
I'm counting all the valence electrons. So I'm counting down here. So 2, 4. So it was just my pink ones were 9.
So we're
1,
not
2,
counting the
4,
outside
5,
ones.
6, 7, 8, 9. The outside was 4 plus 5, which is 9.
4 plus 5. Got it. Okay.
All right. So on this one down here, we're going to break the rule because that's how it is. And there's an easy way to see when it's going to happen. It is when you have, it doesn't actually change any of the answers. So it's up to you. I'm going to draw it again, but then I'm going to show you how it changes after we fill in the box. So go ahead and make your sketch again, right? You have your sigma 2s. You can do the middle part first if you want, and then do your sides. I'm just making another one because sometimes that gets messy. Again, do this in pencil or something that can erase. And then you do your p's. So you're going to have pi sigma, and then you have a big gap, and then you have pi sigma. And your regular atomic orbitals are in between. And then you bracket them somehow. To get full credit, you're always going to just have to draw one time. You're going to have it labeled. So the outside are regular atomic orbitals, so 2s and 2p. And then the center, we have pi 2p, sigma 2p, pi star 2p. Star stands for antibonding or destabilizing, and sigma star 2p. I just draw the diagram once. There's also a way where you just can write it straight across, but I like diagrams. All right, count electrons. And again, and then I'm going to show you how it changes, but it's not going to change any of our answers. So this is not a waste of time. So the question that Major asked is really important. We're going to still, the easiest way for me to explain, we're still counting electrons like we did for the past 2 weeks. So oxygen is 6 and fluorine is 7. So we're still doing their valence electrons. So this is going to be 13. That is why what his question was, we're showing the 2s and the 2p. Does that answer, Major, what you were asking? The two, and we're going to fill in from down here. It's just the 2s's are going to cancel out. All right, OF positive. If it's positive, it lost an electron. So we'll do that one in purple. That's going to be 12 electrons. And OF negative is going to be 14 electrons. All right. So, oh, it's not going to matter. So let's do the pink one. So oxygen is one side, 6 electrons. So back to what question was. So you have 2 and then 3, 4, 5, 6. So oxygen has 6 valence electrons, and the other side, you can do fluorine. So we're always going to just do this with diatomics. There is a way to do it triatomics, and your teacher doesn't know how to do that. You can Google it if you're like really into this. Except the weather's going to be really nice, and so you're going to enjoy the weather too. All right, fluorine has 7. Is halogen. All right, so outside is atomic orbitals, and inside is the molecular orbitals. All right, and again, 13. That is again with the Lewis structures. That was the key. Rocky, you get videotaped. The rest of them don't, but you're in my camera. You're a movie star. All right, go ahead and fill in your 13. So 2, 4. I think the question Major had asked, do you count down below? Yeah, if we're doing valence. So 2, 4, 6, 8, 10. So that gets us to 10. Oh, we're going to 13, 11, 12, 13. All right. And we're going to answer all the questions now. So I'm going to pause. I'm going to let you see if you can answer them, and then take an electron away so you can erase one, see what you get, and try adding one. So I'm going to pause. So if you do these 2 questions first, I should move them first. I always forget to. There is 1 sigma bond. There's only half a pi bond. The anti-bonding destabilize the same type. So these 3 electrons destabilize 3 of these. So you only have 1 1 pi electron left, which is half a pi bond. The bond order then is the sum of your bonds, which is 1.5. You can also do that the bond order equals bonding electrons minus anti-bonding divided by 2. If you want to like feel more mathematical. So you have 6 bonding minus 3 anti-bonding divided by 2. So 6 minus 3 is 3 divided by 2 is 1.5. Yeah. Or you can just add up your bonds. Paramagnetic, because there's an unpaired. Heo is going to be this guy, the pi star 2p. So it's the highest with electrons. And then to do these, there is actually one other question I'm going to add at the bottom. Does it exist? And the answer is yes. The only time the answer would be no, anybody have an idea when it would be a no?
When everything's filled out?
Yep. If the whole thing, if we had, what do we have, 13? If we had 16 electrons, so, because if you destabilize all the sigma and pi bonds, it's gone. So 16 electrons would be neon as a diatomic. So neon as a diatomic can't happen. Neon with a positive charge, they've actually made it. They've made diatomics with the noble gases as long as they pull an electron off. The theory predicted they could do it, and they've been able to do it. All right, we go to a positive, we're going to lose an electron. It is important you lose the correct electron, and you have to lose one of those. So you have two unpaired electrons. They have to spin the same way. Remember those rules from last term? So we still have one sigma. That's pretty easy, right? We have our one sigma bond. This is how you have to word this. You have destabilized half of each of the pi's. So you have two half pi's. So basically somebody ate half of your pecan pie and half of your pumpkin pie. You do not have a whole pie. You have two half pies because you don't want to mix pumpkin and pecan pie. Don't know why, but so bond order is 2. All right, it is paramagnetic because you have half bonds. You have unpaired. If you have unpaired, it's paramagnetic. Highest occupied is still pi star 2p. All right, now we're going to go to 14. Any questions? This is the thing I miss about in person because I can see inquisitive, I can see people's looks and ask. All right, so now I have 14. So 2, 4, 6, 8, 10, 12, 14. This is now diamagnetic. There's no pi bonds left. I've totally destabilized the pi bonds. I have one sigma, my bond order is 1. Highest occupied is still pi star 2p. Does it exist? Yep. Because I still have the sigma bond. As long as I still have something, it exists. All right. So strongest and longest, we have to compare the 3. So which one is the strongest? And they all said.
Is it the OF negative because it has the most complete?
No. That's a good reason, though. I like that reason. It is the most destabilized. So it's actually the exact opposite of what Tristan said. The OF negative is going to be the longest because it is the most destabilized. When you start putting things in the antibonding, you start destabilizing. And that's the key to this theory. It's why it works, is because now we have destabilized stuff. The strongest is going to be the OF positive because it had the least up there in the destabilizing. You can also look at the bond order. Questions? I still have one more piece we have to do. This is not the correct drawing. So we're going to redraw it. It doesn't change any answers. So I want to emphasize that. The answers won't change. So when you do this on the celebration, just draw this start. Just keep answering all the questions. You'll get everything right. But there is one more question, and it is, once you start, what do we have? 2, 4, 6, 8, 10. So when you get to 11 electrons or more, 11 electrons, that means you're in the pi star 2p. The drawing, the MO diagram changes. And it is because it destabilizes the pi's. So we'll write it down as words. You can ponder that next week when you come back and look at this. Again, these are really, they're all the same. You draw the diagram once, you answer the whole study set with one diagram. On the worksheet, on the midterm, it'll be one page, you draw it one time, and then you just keep erasing your electrons. You can draw, you can make it on scratch paper. You just show me one, everything's labeled correctly. So what it looks like, the 2s is the same. I'm just going to do the p's. So the s's are the same. We'll show it to be complete. They don't change. 2s. It's up here in the p's. And what happens? That part of the diagram flips. So what happens is you're going to go sigma pi, and then the destabilized stays the same, pi sigma. So it goes 1, 2, 2, 1. I have no idea. I think this is all theoretical. But the idea is once you start destabilizing the pi's, I don't think the sigma actually moves. I think the sigma stays at the level it was, but the destabilizing of the antibonding makes the pi flip. And so somebody always asked me, well, what if we start filling in? What if we get up to, we had 14, what if we get to 15 electrons? My thought, and again, this is me, I think it goes back to this diagram, because once you start destabilizing the sigma, you've destabilized both. But there's nowhere out there where you find it. And I'm sure you can find really wordy explanations, but if we have, once we get to 11 electrons, this is our sigma 2p, pi 2p. So that's all, that part flips. Everything else stays the same. You fill in the electrons. So to prove it to you, we're going to go back and do the 13 electrons. So 2, 4, 6, 8, 10, 11, 12, 13. Because the part that flips is filled, the thing that changes is up here. So it's when you get that first electron in the pi 2p, all the answers are the same. It's still 1.5, it's still 1 sigma and half a pi. It's still paramagnetic. All the answers don't change. So how I usually ask the question is, it's on the study set. Now I'm not going to remember how I word it, but I think I ask which of the following, and I'll give like 5 things. Which of the following have the flipped diagram or the alternative? So this is, I think it's called the alternate MO diagram. I can't remember the words right now. I had to sit through an hour-long meeting today. I have another one tomorrow morning. So my brain is like not there. And so you would just say yes or no. So these all have the alternate MO diagram. That's what this is. These up here, they do not. Oh, actually, this first one would technically. I'm sorry, this last one, we got to 11 electrons. It doesn't change any of the answers, though. So it's like one question you'll run into. All right, that's all I got. Any questions? I'm going to stop.